Okay, that I good. So see the main thing that you're writing your IDs there. Okay, that is one thing you should keep in mind, that ID number should be there. So here we discuss solutions of this
Sorry, sir, I
assignment one.
forgot to mention my ID number.
Okay, but keep in mind from next. Okay, this is not only for you; it is for everyone, because many are there who are not writing IDs there. So you should write ID from next assignment there. So assignment one, solution. Question number one. Let I show you the question one first. There we go. Find find the real root of this cubic equation using a bisection method correct to 3 decimal places, and hence find the negative root of this equation. Okay, this is the something different thing that we're not discussed in the theory class. Okay, so we'll come to that also. First of all, we have this cubic equation, and it is checked f of 0 negative, f of 1 negative, f of 2 negative, and f of 3 is positive. That is good thing. Okay, so this thing you should mention. Only one thing you can write it here. Hence the root lies in the interval 2, 3. Okay, that is missing. So you should start with that. Hence the root lies between the interval 2 and 3. Now the iteration started. So he started n equal to say 1 first iteration, a is 2, b is 3, and then just a plus b upon 2 is the iteration formula, and it is mainly focuses on the sign. If magnitude is not written, that is also okay, and if you return, that is also okay. It doesn't matter there. Okay, so f of xn is a negative. So as it is a negative, it should replace to the a, because f of a is negative and f of xn is also negative, and that way it is continued. And he got after 11 iteration, it is observed that first 3 decimals start repeating. So 2.706, 2.706, and you'll observe, yes, that's a correct answer. It is correct to the 3 decimal places, and 2.706, that is answer. Now I will tell you the variation. Few of the students got this answer probably in 10th iteration or 9th iteration. That's okay, but you can't say that I got to correct up to 3 decimal places in 3 or 4 iteration only. If you are getting the answer in 4 iteration, it's not possible, because Newton-Raphson method is only the method who give the answer in these less number of iteration there. So here 7, 8 iterations generally we require minimum, depending on how many decimals you are considering, whether you are doing roundup or you are not doing roundup, that also affects to number of iteration. So choice is yours, but the answer will be near about unique. Like here 2.706 is the answer he written. Someone written suppose 2.705 or 2.708. That is also okay there. Okay, so this is considered. Now to get a negative root. Okay, so here I'm surprising that you are getting these answers. Very good. This is just like your self-study you've done. If we have alpha is a root of fx minus alpha is a root of f of minus x, that is a property. So this property, if you know, then you can quickly write the answer. See, the property says that if this alpha is a root of fx minus alpha is a root of f of minus x. So this is the property that we are using to get the root of that other equation. And you will observe that other equation is just f of minus x. If you replace x to the minus x, what is the second equation we given? That is f of minus x. So the root of this equation, f of minus x, this is not correct. This is not f of minus alpha. F of minus alpha should be 0. Are you getting? It should not be written f of minus. Okay, so f of minus x is this polynomial. Now root of this f of minus x is minus alpha, that you should write. Got it? Only there is a small correction at the end. So instead of f of minus alpha, you should say minus alpha is equal to this one is the root of that f of minus x. Any doubt, anyone in the question one?
No, sir.
No doubt. Sir. Okay. So only the last line is not correct. Otherwise, everything is correct there. So question number 2 then. Question 2 is again a bisection method we have to use to get a root of sine x equal to 1 by x.
Excuse me, sir.
And yes.
Sir, in question number 1, there are two different equations.
They're not different
Sir,
equations.
there it is -9 and there it is +9.
So I'm saying this is f of x and this is f of minus x. Are you getting?
Sir, there it should be +4x. Then.
No, you check. See, let I show you. You have to write the equation fx equal to 0 and f of minus x equal to 0, and then you can check it. Okay, so I'll show you here. This is our fx. I'm saying. Just a minute. So this is fx. Okay, so I will take f of minus x equal to, this is fx equal to 0. Now we have to write f of minus x equal to 0. Just replace x by minus x everywhere. So minus x cube is minus of x cube, is it? Then minus plus 4x, got it? And that -9 as it is. Now this equation and this equation is the same. Because it is equal to the 0, just if you take -1 and merge that minus on the right side, you get x cube minus 4x plus 9 equal to 0. Are you getting?
Sir, can we do it separately by using this equation?
Why you are going to do the 9 or 10 iteration again? Your question is already given, na? Hence find the negative root. Hence ka matlab hai using this. Okay. So when we said this alpha is the root of this fx minus alpha, that is minus 2.706 will be the root of this equation. That is the direct answer. It is in one line answer. Yes.
Okay, sir.
We can do with the property, that's fine, but can we find with another method the roots, because it's not mentioning here like you have to use bisection for second question. Like,
no, the question is straightforward. It is written hence find. Hence ka matlab by using that way only. Are you getting?
okay, sir.
Okay. Otherwise, yes, there are multiple ways. You can go by Newton-Raphson. You can go by hit and trial. Number of ways are there, but you should understand the question first. In the question itself, it is written hence find. Okay, that's all. Come to the question 2 now. The best part of the question 2 is we are given everything. First of all, we are given the interval. The interval is 1 to 1.5. Stopping criteria also given. We have to do the 7 stages, that is 7 iteration. And you'll observe trigonometric term appeared in the equation. That equation pictured as x sine x minus 1. That is our fx. Fx is x sine x minus 1. That is the fx. And trigonometric term appeared there. Hence, we should do the calculation in radian mode only. And the answer is here 1.11328. Let me see whether I done correctly or not. So question number 2. 1.5, this is already given. Just you have to check whether f of 1 is negative, f of 1.5 is positive. Yes, the root exists there in between. And after near about 7 iteration, you got 1.1132. Okay, that's correct answer there. Got it. So this is just table here. But remember, this formula writing is very important here. If you forget to write the formula and just return the answers there, it's not good. So formula is also important. You should mention there. That about question 2. If anyone have a doubt in the question 2, yes, you can ask. So come to the question number 3 then. Use a false position method to find a real root of this equation. I think this question we done in the class, is it? We already done this question in the class, and that is correct 4 decimal places. So fx is x log x minus 1.2, and yes. Okay, this question we done by Newton-Raphson method actually, but here we have this question is by a false position method. So for false position method, let me see how it completed. So x log x, yes, x log x minus 1.2. So x is a f of b minus b f of a upon f of b minus f of a. See, he checked f of 1. F of 1 comes a negative. F of 2 comes a negative, but f of 3 is a positive. Okay. Now we have to use a log tab from the calculator because it is the best 10 for calculation. F of 2 negative, f of 3 positive, a, b are taken as a 2 and 3. And then they use the formula that a f of b minus b f of a upon f of b minus f of a. Here you will observe after 4 iteration, the answer comes correct up to the 4 decimal places, which is 2.7406. 2.7406. That's correct. Good, very good. And this is the way you should write in the final exam also. Only the thing that is missing everywhere, that nowhere mentioned in which interval the root exists. So here one line is required that should say, thus the root lies between the interval 2 and 3. That. And the last question then, last fourth question of the tutorial, use a false position method to get a fourth root of 32. Yes, few of the students have the doubt before how to write the equation, but yes, we discussed that in the class also. As fx is, we want as x equal to 32 raised to 1 by 4. So it is x4 minus 32 is 0. F of 0, f of 1, f of 2, f of 3. But f of 2 is negative, f of 3 is positive, root exists in 2 and 3, and then the iteration proceeded, and you got the answer as 2.377. I think that's the correct answer. Yeah, 2.377. That is the answer. Good. Any doubt, anyone in the any of the question of the assignment 1?
No, sir.
No, sir.
No doubt. Okay, good. Okay, just a minute. I'll check whether this. So I recorded the solutions for this tutorial also, or assignment also. I will just rename it and I will share you later on. Okay. So come to the today's topic then. So the second topic that we are going to start is finite differences now. Again, for finite differences in final exam, roughly you will get a question for 7 to 10 marks. 7 to 10 mark questions will come from finite differences. So where you will get 2 mark questions, like you have to find out some relation between the operators. Okay, derive some relation between the operator. So that is a 2 mark question. And later on, the question may comes, just prepare the forward or backward difference table for 2 marks. So that is also possible. And interpolation mainly comes for 5 to 10 marks there. We'll come to that interpolation later on. So first we'll see why these finite differences are required to us. So the purpose of this finite differences is, first of all, our function y equal to fx is not given explicitly. The function y equal to fx is given in a table form like this. So instead of giving values of instead of giving function fx equal to sin x, fx equal to sin x, instead of giving that fx is a log x, instead of giving fx as some combination, say x square plus log x plus tan x, something like that, a little lengthy function. So instead of giving the function this explicitly like this, we are given some table values only a table values, say x0, y0, x1, y1, x2, y2, x3, y3, and xn, yn. We don't know what that function is. We don't know what is fx. But we some values. how to decide that function? What is that? Suppose I given some values, say I given x and y. So x is say 1, y is say 1, x is 2, y is 4. Okay. Now, can anyone tell me what should be the function which satisfies these values?
Square.
Okay. Someone said y equal to x square. Okay, say y equal to x square. Yes, right now, because these values are the, you can observe some relation, and by observation you predicted y equal to x square.
So we can go
But
through the differential method, like slope method.
yes, correct. Not necessarily y equal to x square is only the relation which satisfies this value. Right now, if you take 2-point formula, you can get an equation of a straight line which passes through these 2 points. So you get linear equation also. Now, what is the logic behind that? Behind the finite differences? The first thing I want to say that this function can be approximated by a polynomial of degree 2. Right now it is 2. Actual function is 2. Actual function, suppose y equal to x square is actual function, but I can get the function like a straight line also, straight line equation also. For example, y minus y1, that is y minus 1 upon y2 minus y1, 4 minus 1 is 3, x minus x1. I think I made a mistake. Yeah, correct. So x minus x1 upon x minus x1 is 2. So you'll observe this is y minus 1 upon 3 is equal to x minus 2 upon 2. X minus 2 upon 2. This equation also satisfies these 2 points there. Okay, that is other thing. Come to the one important article that you learned in the last semester. How many of you know the Maclaurin series or Taylor series? Yes, what is the Maclaurin series? Anyone knows the Maclaurin series of a sin x? Have you learned that?
We don't remember.
You don't have that in last semester.
Yes, sir, it was.
So we didn't have this.
Okay, it was removed. Okay, then forget. Just I want to tell you what is the purpose of this Maclaurin series. Maclaurin series gives us algebraic form of all the functions. So sin x is x minus x cubed by 3 factorial plus x5 upon 5 factorial and so on. Log x is, yes, it is say probably it starts with 1 plus x by 2 plus, okay, something like that. I am not going into detail. So this log x, tan x, everything can be written in a series form, in a power of x. So indirectly, what I want to say you here, that every function of x, yes.
So we have a series for log x plus 1, not for log x.
Yeah, correct. X plus x. I forgot it. That series right now. X plus
X,
is
so
it
minus x square by 2.
Is it alternate plus minus is there?
Yes, sir.
Okay.
Some
So,
in chat.
no, not required actually. We don't want series right now. Any particular series. Just I'm giving you hint that every function can be written in a algebraic form, or ignore the higher degree terms. Suppose you ignore the 7th and higher degree terms. So sin x can be approximated by a 5th degree polynomial. Sin x can be degree polynomial. Similarly, this also can be approximated by some 5th or 7th degree polynomial. Okay. So the same thing we are going to do it here. Here we have in finite differences later on that each set of data we are given values. Suppose we are given n pairs of xy. If we are given n pairs of xy, we are going to approximate that data by n minus 1 degree of a polynomial. I am repeating, whenever there is a n pairs of xy are given, they can be approximated by n minus 1th degree polynomial. Okay, and once we get that, once we get that polynomial, we can predict the values of at unknown places. Okay, we can use it for prediction purpose, and indirectly we know the functional nature completely there. Okay, so in finite differences, why the word differences is again used? This differences word is much more similar to the derivative. Okay, this is a differentiation. Differentiation and differences goes in a similar way. Only differentiation we use it for continuous function y equal to fx, and the difference word we use for the discrete function, which is done in number of x1, x2, y2. So difference and derivative are similar only. We'll come to that also. Okay. So what are the important things where this table one? The difference between two successive values of constant. Suppose you take x1 minus x0, you get some number h. Okay, then you x3 minus x2 should be h again. So values of xi should be equally spaced. That is the requirement. And then the approximate is by x1 degree polynomial. Okay, so that is happening in a finite differences here. So come to the main thing now. Yes, there is a similarity between derivative and differences we already discussed. Now this is the starting part of differences. First, we have few difference operator. This difference operator, there are roughly 4 difference operator that you have. So we use it for interpolation purpose later on. Interpolation, we'll see what is interpolation also in the next session. So first difference operator is forward difference operator. Okay, the important thing you should remember the notation. The notation of this difference operator is delta, this capital delta. You will observe this is the notation delta. So delta of fx. Delta of fx is f of x plus h minus fx. What is the definition of a derivative? Can you recall it? What is a derivative? Suppose I want f dash x. What is it? What is f dash x in equation form?
F plus h minus fx by h.
Very good. It's a very good answer actually, because many of the students forget. Many of the students forget the actual definition of derivative, and they just know. They know the derivative of sin x is a cos x. But if I ask you how that a derivative of sin x is cos x, or what is the actual definition of derivative, many of students not able to give it. But yes, this is the good thing that you recalled it. It is similar to this only. Okay, f of x plus minus fx upon h. If we take it is instead of delta fx, we can say it is f dash x. So these are like a derivative only. They are like a derivative only, but they are defined on number where h is a very small, when h is a very, very small, then it becomes a derivative there. Right now, it is a differences only. Okay. So next value minus same value gives us a forward difference there. This is one of the notation. Other notation is this also. If write the values of y as y0, y1, y2, y3, and yn. Delta yn is yn plus 1 minus 1. So about definition for forward difference. Okay. So delta is a forward operator, and it is defined like, you should remember like that. We come to this part. Now come to the next operator, and that is a backward operator. Now you'll observe this backward operator is denoted by a same notation, but it is a triangle is a reverse. It is read like a del. This is delta. Okay, remember this is a delta, while this is a del. Okay, so del fx. Del fx is the same value minus previous value. The difference. So del fx, it is a backward operator. Backward difference we are taking. So when backward difference is same value minus previous is a backward, while next value minus same value is a forward. Okay, so that about second operator that we have. Come to the third operator. Third operator is a central operator. Remember, these two operators are very important for us. The first two operators are very important. Central operator will not require that much, because just in our syllabus it is given to introduce central operator, but central interpolation is not part of our syllabus now, so this will not require anywhere. So you'll observe there is a little bit similarity in this definition, and this definition. F of x plus h minus x is denoted as a delta fx only, but delta fx, and this is a small delta now. This is capital delta. This is capital symbol small delta, lower delta, you can delta of f of x plus h. Only the function is this function defined at some different point. Okay, this function is defined at x plus h by 2. That is a central point. Suppose that we have x0 and x1. So it is defined at the point here, x0 plus x1 or x0 plus h by 2. X0 plus h by 2. So that function is defined at center point. So that is a delta operator. So you'll come to these things with calculation. We'll come to that later on. Just the last one, it is a shift operator. The shift operator is denoted as a E. The purpose of operator is just to change the function effects to the with n points there. So if you take, say, I'll write it here. Suppose I write e square of fx. Okay, suppose I have this as a 0, e square of f of x 0, and we have and say 0, x1, x2, x3, and so on. So e square means we have to instead of writing the functional value at x0, we write the functional value at two shifted points. So x0, x1, and x2. So I will say f of x2 is actually 0 plus 2. I hope you are getting. E square of f of x0 is f of x2. In general, this en of fx, provided it is 0 here, x0, then it is f of xn. Here it is e raised to n of fx, that is f of x plus nh. Okay, x plus nh, that is the formula you have there. Okay, so that about the 4 operators. All the 4 definitions you have to remember, definitions of these operators. Now come to the higher order forward differences. Suppose this is the data that we have, values of x and y were given. Let I write first few of the differences here. Let I write first order difference. So I will take delta y0. Yes, anyone? What is the value of delta y0?
So y1 minus y0.
Y1 minus y0. So we are taking delta of y0. So next minus the same value gives us a delta y0 there. Okay. So this is first order. This is the first order difference. It's just like first order derivative. Okay, you can compare like that. If I want order derivative, actually second order difference here. So I will write like this: delta square of y0. So to get delta y0, we can do like this: delta of delta y0. So we are operating this delta operator 2 times, delta of delta y0. So our delta will be as it is. Delta y0 already calculated. It is y1 minus y0. So this now take this delta operator inside, delta y1 minus delta y0. Now delta y1. Yes, what is delta y1?
y2 minus y1.
Minus y1 already. If we simplify this, we get y2 minus 2y1 minus y0. Second order difference. Plus y0. That's good observation. Very good. So the second order difference can be written as delta square y0 minus 2y1 plus y0. That is a second order difference there. Similarly, can calculate higher order differences, say third order, fourth order. Just you by 1. Okay, it is by 1. But getting all these difference values becomes a very simple from the difference table only. Table is always better to get all the difference values because it is all possible differences which exist there. So we'll come to that part also here. So this is the forward difference. Forward difference table is given like this. You'll observe the first thing that here these values of x and y are always given. So these first two columns are always given because we have the pair of xy values there. Pair of xy values. So x0, x2, xy, x4, y4. This is a given. when we delta y, so the delta y0, it is y1 minus y0. Actually, this is a way, generally I prefer to write the table. So when the values of xy given, just we write it in alternate rows, alternate lines of your notebook. Okay, if it is a ruled pages, on the ruled pages, you just leave one line there, so that at the center you will write this number. What is this delta y0 actually? This delta y0 is just y1 minus y0. If you subtract y on calculator, you write it here, this is delta y0. Similarly, here you write delta y1. Why is the delta y1? y2 minus y1 you write it. Or delta y2, y minus y2. This delta minus this order derivatives, first order differences, first order differences, because it is a. So next, now we want delta square y0 value. To get a delta square y0 value, just you have to do it this number minus this number. This delta y1 minus delta y0 gives you delta square y0 derivative. This number delta y2 minus delta y1 becomes delta square y1 and so whenever we take a forward differences, when we take the forward difference table, maximum number of differences exist for y0 only. Observe how many differences exist for y0. First order, second order, third order, and fourth order. So maximum differences, which is a fourth order difference, which exist for first number or first pair which is given. But if you proceed further, you'll observe here are 4 differences, but for x1 y1 or for y1 there are only 3 differences exist. For y2 only 2 difference, for y3 there is only 1 difference, and for y4 that difference does not exist only. If we want delta y4, say delta y4, what will be a formula? What will be a formula?
y5 minus
y minus y4, but y5 is already unknown to us. We cannot get that delta y4 only. Delta y4 does not exist there, does not exist because y5 is not given. So this first row, remember this first row is a very, very important row in the forward difference table that we require later on, and this row is known as a leading differences. This is a row of leading differences, and these leading differences only we require in interpolation. Okay, later on you learn interpolation. So that time only the first row is important there. We'll come to that in the next session, mainly on interpolation. So you can see the example now. Example for a forward difference. They are very, very simple here. So here is an example. Here is a question on the screen. We are given the values of x and y, and the question is find delta f of 10, delta square f of 10, delta cube f of 20, delta 4 f of 15. Remember, this type of question was not asked in previous question paper. Okay, last 4-5 years, not this example is asked, but this table is obviously in interpolation with this table. So instead of calculating it separately here, we make a table. It's better to write a table. We can have these values which we require. So what is step one? Step one, we should write these values of x and y in a column form. Okay. So here is a first step. Step number 1, you will observe x is written in the first column, y is written in the second column. Now we want delta y. Okay, the first order differences. Can anyone tell me just delta y0? What is delta y0? This is x0, y0. So what is the delta y0?
So 1.54.
1.54. 1.54. Let me check. Is the correct answer. So this way, all these values you can calculate. You will get the first order differences by subtracting only this number minus this number. You write down in middle. Okay, that way. So we are proceeding only again. Second order, third order. Okay, I think I missed here. So I missed one column here. Third order differences I not written. Okay, this is my mistake. I have that. File with me. Let I show you. I think this is the question. Yeah. So you'll observe third order differences are here. So this I missed, this column I missed there. Got it? Now, from this column, we want these values. You'll observe the values we are interested. We are interested is delta f of 10. Delta f of 10. So where is 10 first? And this is delta of 10. For delta f of 10 is here. Got it? So we can write delta f of 10 is equal to 1.54 directly. Then delta square f of 10. So this is f of 10, delta f of 10, delta square f of 10. So this answer is also for delta square. So that is directly. Now this is not there. So it is a delta cube f of 20 we want. So first you should say here this is f of 20. This is f of 20. This is a delta f of 20, delta square f of 20, and delta cube f of 20. So this is a delta cube f of 20 that is for third bit. Delta cube. And lastly, delta 4 of f of 15. So this is 15. Del f of 15, del 15, del cube, and del 4. So the answer of this last is here. Got it?
Yes, sir.
Yes, sir.
This way, you can get the values of the forward differences. Now, here is a little different question that we have to construct the difference table for fx for x equal to 1 to 5. So instead of giving x0, y0, x1, y1, we are given the values of x as 1 to 5. This is x0, x1, x2, x3, x4 given. Y0, y1 value is not given, so we can calculate from this equation. So x is 1, then y is say 4. So x0 is 1, y0 is 4, that way. So this is x0 to x4, and this y0 to y4, and difference tables. I want one good observation from this table. Can you tell me something, some special thing from this table? Let me see who have the good observation here.
Sir, delta 4 is equals to 0.
Delta 4 is 0. Why it is 0? Why it is a 0?
Sir, it comes a constant there.
Previous differences comes constant, is it? Previous differences become third order differences are constant, and fourth difference is 0. So it is exactly similar to the derivative. You'll observe this is a cubic polynomial. Why it has happened? Because we are given a cubic polynomial, and for this cubic polynomial, we know the third derivative is a constant. Third derivative is a constant, and fourth derivative is a 0. And that same thing has happened. This third order is constant, and fourth derivative is 0 because it's a cubic polynomial. Okay, so this generally happens there because it is differences are similar to the derivatives there. You'll observe the nth difference of the polynomial of nth degree are constant. So that is same thing I'm saying here. It is a cubic polynomial, so third derivative should be constant, third difference should be constant. Last slides there. Here, y0, y1, and we have to the difference. So should be the polynomial which is approximated this these numbers. We don't know the polynomial. Now this is a reverse situation. We are given x0 to x4. We are given to x4, and corresponding y0 to y4 is given. Okay, we create a difference table. But after observing this difference table, can you say me what should be the degree of this polynomial?
You can take it by the slope method, and then
no need of slope. Right now, degree should be 3. Third difference is a constant. You love the third difference is constant. Difference is a 0. So yes, it is approximated by a third degree polynomial. Simply, you can say. Okay, this actually there is some cubic polynomial, and that we can get in interpolation. There is a cubic polynomial. We can get it to fix this data. Okay, to fit this data. Okay, that unknown polynomial. That we can find it here. So last two slides, and it is just repetition of a forward. Okay, we come to the backward difference table. Now, what is the difference in forward and backward difference table? I will tell you the difference is only this first notation. In forward differences, when I say y1 minus y0, what we say y1 minus y0 is a delta y0, is it? We say delta y0. Actually, in forward differences, we take the differences from beginning of the row. So we say delta y0, delta y1, delta y2, and so on. So when I say y1 minus y0, it is delta y0. y2 minus y1, I will say delta y1. This y3 minus y2, delta y2, so on. But in backward, actually, we started difference from the bottom here, from this side. So we say y5 minus y4. y5 minus y4 is a del y5. Okay, this is del y5. So y4 minus y3 is a del y4. y3 minus y2 is a del y3, and so on. So that only. So the table remains same. Actually, here is same number, but that same number have some. Suppose here I get 8. Suppose I get 8. So this 8 is nothing but delta y0 is 8. Delta y0 is 8, but not only delta y0 is 8. Del y1 is also 8. Del y1 is also 8. So the same number have the another interpretation with forward and backward. That's one only. And in backward interpolation, you will observe maximum differences exist for the last row. The last row, how many differences is there? Delta y5, delta cube y5, delta 4 y5, and delta 4 y5. So y5 have the maximum differences, while y0 doesn't have the difference. You will observe delta y0 also not. Del y0 doesn't exist. Del y0, del of y0 does not exist. Okay, so backward differences exist maximum for the last row, and that row is known as a leading row. This is the leading row for the backward operator. That's one. So here is a difference table. You will see form of difference table, and you should write these values. So difference table is prepared exactly similar way. So 204 minus 184 is a 20. That way we want see which values we are interested. We are interested in the values of this one, delta square y70. So first see, it is a 70. This is f of 70. Okay, this is f of 70. Now we want del. So we want del means we have to go this way. Okay. See, when we want rows of this is the row for delta. Sorry, delta, my mistake. Delta rows will go like this. Got it? I hope I'm clear here. So we want del square of y70. So this is f of 70. This is the del of f of 70. This is del square of 70. And this answer of the first is 2. 2 is the answer. Delta 5 y90. So this is f of 90. This is del y del square, del cube, del 0. Okay. So that's for today. There are similar questions.
Solve step by sir. I'm not answer.
No, a table you have to prepare like that only. There is nothing step by step. You just when you practice now, when you practice for assignment, definitely you'll get all these things. Only the thing is, first you have to write these XI values in the column form. Once you write in column form, take the subtract 204 minus 120, 226 minus 204, 22. This subtraction is written here. And only important thing, what this number indicates is matter. That is what we are interested. That is matter again. That matters. For example, suppose I'm interested to get say delta say y50, delta y50. So I have to come to the 50 first. This is f of 50, delta y50. Okay, because for delta I will go this way. This is delta. So answer is 22. But if I'm interested to write say del, del of y70, del of y70. Now to get del of y70, I come to the 70. This is f of 70, and now for del I go this way, and this is a 24. So this is 24. That way it is answered. So same calculation, same table, only notation matters. What you are writing, that matters there. Okay, so that's for today. I want attendance from Seer.